Hello, everyone. My name is Alexandra de Castro, and this is a replay of our latest Perceval and Cloud webinar. This was the webinar number 5, and it was held on the 18th of July. And actually, many people attended, but unfortunately, we had serious problems with the recording and we could not recover the video. So we decided to recreate the webinar and upload it to our YouTube channel so that our audience don't miss anything. So most of you probably don't know me well, so I'll start introducing myself. I am a theoretical physicist by training and work as a research scientist for about 10 years. And after that, I left academia and I discovered my passion as a science and technology communicator and never looked back. And actually, I have been doing this for around 10 years also. I joined Quandela about a month and a half as an engagement manager, actually already 2 months almost. And I am your point of contact with Quandela Cloud. So I will be hosting this series of Perceval and Cloud webinars. So normally before we start our webinar, we go through the rules, but since we don't have audience today, we will just skip that part and present our team. And also our team is different for this recording, but I wanted to show you that we normally have our marketing lead, which is she's making these events happening. Jan and Eric, who are our experts on the cloud and Perceval, so they are usually with us to help us answer your questions. And we have our IT expert in charge of the streaming, which is usually Maxence. But today it's just Sam, Samuel, and I, and this is Sam, and is our applications engineer, our star speaker. So this is what is going to happen. First of all, I'll take some minutes to give you the latest news on Perceval on the cloud, and then Samuel will have the floor for his talk and demonstration. Our community keeps growing, and we are very happy to share that we have circa 800 users. And especially, I want to warmly welcome our academic plan users from the University of Yale and Northeastern University, both from the USA. And since we held our live webinar, latest live webinar, we also have a new academic plan user from Colombia, from la Universidad del Valle in Colombia. So very welcome to this new user from so far away from the planet. And I want to show you also the increase on the spending of our cloud users on our devices on the cloud, and they are running and running more and more jobs. And because I didn't want to crowd the chart, I only include two simulators. Mostly SimAlter is people use the most. And then we have our QPUs, Axila, which is not operational anymore, and our new QPU Alter, which is, as you can see, people using it is increasing the usage of this QPU. And of course, the total, including all the simulators and QPUs and all. And you can see how the usage has been dramatically really increased. So we are very happy about this. And I wanted to share with you how diverse is our community. Our community is very diverse. We have people from universities, from academia, people that enthusiasts using the cloud and learning quantum, and from companies, from big companies, from small companies. We have people from all over the planet, in the university from Brazil and China, from all over Europe, and from companies we have from many industries: energy, finances, aerospace, logistics, healthcare, you name it. So we are very happy about this. And these are our news, our updates on the Cloud and Perceval. So we just released our Cloud update 2.0.4, and it has many improvements. I just listed 4 here. Speed on the jobs listing page, QPU characters readability, and that the user now can export their invoices, and they fix some boxes, some box, and we have well, usually we have Jan to answer the questions. This is why Jan is here. To help us answer the questions on these new releases. But anyway, you can always reach out to me as your engagement manager for any question that you may have. And we have also some novelties on the our open source Python-based platform, Perceval, that you can use to program Quantum. And we have this new release. Is called Sir Gawain, and it's our release Perceval 0.11. And the highlights are we have our new photo recycling method, which is a novel noise mitigation method. We have this new feature that you can send post-selected or heralded circuits directly from local simulations to the cloud. And you can have now available a strong simulation backend, approximate strong simulation backend. And the full release, you can see it in our GitHub. And we usually have Eric, which is our Perceval expert, answering your questions on Perceval. And so now we have Samuel, who in our webinar number 4, which is already available on YouTube, he showed us everything about the new cloud release and how to use it. And today he's going through, he will go through the toolbox, and he will explain what is that, and through our algorithms and how to use them. And he actually will demonstrate some how to tackle some of the use cases with our cloud. So Samuel, now you have the floor.
Thank you very much, Alexandra. Okay, I'm just gonna share my screen as well. And then, okay, so now we're back on the same slide. So yeah, so as Alexandra said, today's workshop or webinar is all about the Quantum Toolbox, which is one of the features of the Quandela Cloud. So before we go into the demonstration of the toolbox, I want to just give you a quick overview of what the toolbox can do and what it contains. So here you see all the algorithms which are at the moment available on the Quandela Cloud in the Quantum Toolbox. This is a list which is the current state, and of course we will keep adding new algorithms to it. But for now, I will walk you through what these means and what you can do with them. So as of now, we have 5 algorithms, and I grouped them in 2 broad categories. You can see here the 3 blue ones and the 2 purple algorithms. So let me start with the blue algorithms. These are all VQE-based algorithms. So VQE stands for Variational Quantum Eigensolver, and that's a very popular quantum algorithm. And the main thing you can do with that, you can calculate the ground state energy of a given Hamiltonian. But there are different versions of it, and that's why we have 3 different algorithms in our toolbox based on that algorithm. So the first thing is we have the VQE chemistry, where you really directly calculate the ground state energy of a molecule. And that's also a very, very common use of the VQE algorithm. So here, basically in the toolbox, you don't have to think about how you get from the molecule to some quantum description. You can just insert the molecule you would like to calculate the ground state energy, and then the algorithm in the toolbox will take care of everything and will just give you the final result of the ground state energy. As of now, we have 3 molecules implemented. So we have BeH2, LiH, and H2. as the 3 molecules you can directly calculate on the quantum toolbox with this algorithm. But again, here there'll be more molecules added to as we go along. So keep an eye on it, and you will see if there's an update. Then, as the second VQE algorithm, we have the VQE custom, and that is basically the same algorithm as the VQE, but gives you a bit more flexibility in what you want to calculate with it. Because here you don't insert a molecule, but you insert a Hamiltonian. So the Hamiltonian is basically the equation which describes the energy of a system. And for example, the energy of a system of a molecule, but it doesn't have to be a molecule, and it doesn't have to be one of the 3 molecules we have included in the chemistry VQE algorithm. So here the user can really completely freely choose which Hamiltonian they would like to use, and then get the ground state energy of that Hamiltonian. So if you want already to try some new molecules, which are not available yet at the chemistry VQE, you can already insert them here in the custom VQE and see what the results are. Okay, so these are 2 of the VQE algorithms. And then we have a third one, which here we have, it's called CVAR VQE. And that CVAR is an extra version. So this stands for continued value at risk and variational quantum eigensolver, of course. And here, that is a optimized version of the variational quantum eigensolver algorithm. So it's actually a different algorithm than to the one we used at the chemistry and the custom VQE. And it is optimized for certain optimization problems, and specifically for so-called QUBO problems. QUBO stands for quadratically binary optimization. And here, quadratically unconstrained binary optimization. That means in the Toolbox algorithm, the quantum from our Toolbox, you insert directly the problem in a so-called QUBO matrix. So you have the possibility to insert your problem directly as the QUBO problem, and then the CVAR VQE algorithm takes that and calculates the result of that. So the whole point of all these 3 algorithms is that we want to make it as easy as possible for you as the user to insert your problem in a very simple way, and then let the toolbox do all the hard work, and you just get the result. So you don't need to know how these algorithms actually work in detail. Of course, you can read up on it, but to use the toolbox, you do not need to know how they work, and you can just use them as a plugin. And that's the whole point of the toolbox, that even people who are not quantum experts can directly access these state-of-the-art algorithms. Okay. So these was the 3 VQE-based algorithms. And now we have also 2 graph-based algorithms. So first thing I want to talk about is what is a graph? Because graph has in mathematics 2 meanings which are completely different. And if you're not have a strong mathematical background, you probably think of a graph as something which has an x and y axis and some lines in it. But that's not the graph we are talking about right now. The graphs we're talking about now, you can think more about it like a network. So you can see some of these symbols on the slides here. This is a better picture of what the graph in this sense actually means. So a graph is just a collection of points, nodes, and lines, edges connecting them. So you can think of them representing, for example, a social network. So if you think about all your friends, each friend would correspond to a point. And if 2 friends know each other, then there would be a line in between. And that would be a graph. That's how mathematicians think about graphs. Okay, I'll show you how that looks in a second again. So don't worry if that was not as visual yet. But just so you're aware that this is the type of graphs we are talking about. Now, for the 2 algorithms here, we have the graph isomorphism algorithm and the dense subgraph identification algorithm. And both of them take as an input a graph and then calculate a certain property of that graph. Or actually, in the case of the isomorphism algorithm, you take two graphs as an input and then calculate a property which relates the two graphs. And I'll talk more about that. And so with that, that's a native photonic algorithm as well. That's important to point out here. So as you know, we are a photonic quantum computing platform, and here the graphs algorithm make direct use of that photonic platform. Okay. So now we're going to go and look at one of these algorithms in a bit more detail. And I've chosen the graph isomorphism algorithm to illustrate how it works and what it actually can do. So let me go to the next slide and we'll talk about that. So here you see two graphs, graph A and graph B. So now you have a picture of what I was explaining before. A graph is just a collection of points, in this case 4 points, and then there's some lines in between. There can be loads of lines in between or less. It's just different graphs. These lines are called edges. How we have multiple graphs. And now you can see in these two graphs, I've written down the edges at the bottom. So the way I described an edge is always a pair of two nodes, 2 points, which are connected by a line, by an edge. And the question is now, these two graphs, do they have the same properties? Do they have the same overall structure? And that is what is meant by the word isomorphism. Isomorphism, again, is a word from the mathematicians' world, and it just means, in a very precise way, means are two things the same, but in a structural sense. So in this case now, we have two graphs, and the question is, are they the same? So of course, they are not exactly the same in a sense if you look at the labels of the graph, like the numbers, they are not in the same order. But that's okay. For what we are really interested in is the structure of the graph. So for example, here in this graph A, we have 3 nodes which are all connected with each other. In this graph A, it's the nodes 1, 2, and 3. And in graph B, we have the same substructure here. We have also 3 nodes connected all with each other, but it's the nodes 1, 4, and 3. So these two graphs, 1, 4, 3, ignoring on graph B, ignoring the point 2, and on graph A, the graph 1, 2, 3, ignoring the point 4, they would be actually isomorphic because they're exactly forming this triangle and everyone is connected with everyone, even though the labels are a bit different. But now we have a fourth point in both of these graphs connected to one of the other points. And now the question is, are these graphs now the same? So I'll let you think about that a little bit, and I'll come back to the solution at the end. So the question is, are these graphs isomorphic? And that's exactly what our algorithm, the graph isomorphism algorithm, can determine. So let's start with the demo. So I'm going to go to the quantum cloud, and we're gonna try out this algorithm directly. So here we are now on the dashboard of the quantum cloud. I'm sure many of you have seen this before on your own account. So let's now go to the Quantum Toolbox tab. So if you've not tried this one, here it is. And then we're going to have a look. Okay, graph isomorphism. So we open the API description. This is how you can access it. And now here we have our place where we can insert our graphs and use the algorithms. So here we have this box where we can start inputting our data. So the first thing we have to do is we have to put a fresh token in. Let me delete what was here already because this is probably not the correct one. So first we have to go back to the cloud, go to tokens, and okay, let's create a token. So we call it Cloud Demo. We'll make it available for maybe just 1 day, because we only need it for now. And now we've created a new token. So let's copy that. And now we can input it into the isomorphism or the toolbox field. And now we can go to the body. And you can see here there's different input parameters we can set. So the first thing is we can set an algorithm type. And if you actually look here, there's two options, Laplacian PP, which stands for permanential polynomial, and just PP, which also stands for permanential polynomial. And basically here, the Laplacian algorithm works just a bit better. Both of them do the same thing, but there's actually not much reason to use the standard PP. If you want to know more, you can read about it in the paper, which I link in the end. Then we have another parameter, the epsilon parameter. Again, here, that's a parameter. The 10 is already kind of chosen to be a good value. You don't really need to change it. If you want to know exactly how it affects the algorithm, you can read about it in the paper. Then we have a parameter called error. And here, this is maybe a good point to explain you a little bit how the algorithm works under the hood. So the way these native photonic algorithms work is that we are calculating a mathematical property of a matrix. And this property is called the permanent. That's why also you've seen permanential polynomial. So the permanent doesn't matter too much exactly how it's calculated, but it's just a number of a matrix. And what we're doing in these algorithms, we are calculating that property, the permanent of the first graph, and we're calculating of the second graph. And then we compare the two. And if they agree, then we know these two graphs are isomorphic. And if they don't agree, then we know that these two graphs are not isomorphic. And this error basically says how much do they have to agree? Do they have to agree perfectly, or can they disagree slightly and we still count them as agreeing? So you could think, oh, but let's put it to 0 because we want to have them agree perfectly, so then we know they are isomorphic. And in an ideal world, that would be the case. But of course, we're running this algorithm on an actual hardware, so there's some noise. So if we would set the error to 0, we would always get the result that the two graphs are not isomorphic, even though sometimes they of course are. And that's why we need to have a small error. So you can play around with it a little bit and see what the differences in error mean, and at what point you will get maybe wrong results. But for now, I will leave it at 0.1. Okay. Now, the next input, and maybe I'll delete what we have right now, is the graph A. So the graph has this structure of these edges. So we have the first edge, then the second edge, and so on, and a list of all these edges in exactly this format. And it's important to keep that format because otherwise this algorithm will not work. And okay, here I forgot to delete this. And then we have exactly the same with graph B. So here again, we can just copy this because we in the second want to insert our own graphs. So that's why I'm deleting here these ones. Sorry. There we go. And then in a second, we will enter our edges for our specific graphs to see. But let's go through the other parameters. So here we have a parameter called max iterations, number of samples min accepted, and the platform name. So let me start at the bottom. The platform name is the platform you want to use on the cloud. So if you want to use our QPU, you have to change sim to QPU. And if you want to do a simulation, you keep it at sim. And then here you enter the platform you want to use. So in my case, I want to use SimAlter because Altair is our new quantum computer. So I want to simulate now SimAlter, but I could also run the same algorithm on the QPU by just changing sim to QPU. Okay. And now let us go back to these 3 other parameters. They actually all kind of go with each other. So if we remember again, how does the algorithm work? As I said, we are calculating the permanent of that graph. And for that, we need many samples. So this number of minimum accepted sample, that's how many samples we need or we want to have in order to calculate that permanent. So if, of course, we have more samples here, the precision will go up because we have more information for the algorithm to calculate that permanent. So 100 maybe is a good number. Maybe you would like to have it a bit more precise, or maybe you want to see if you can get the good answer also with less samples. You can play around with that. And then the number of samples max iteration is related to how long it will take to get these samples or how you get these samples. So basically what it does, the number of samples is the number of samples the algorithm tries to get at one time, but then there's some post-selection happening. So maybe out of this, in this case, 10,000 samples generated, not all of them will be accepted. So then we have to try again. And that is the number of max iterations. So in this setting, we will try a maximum of 30 times, and then we will stop the algorithm. This is a bit overkill for this example, but that's okay. It doesn't hurt us. And basically, as soon as we've collected 100 samples, we will stop. So in our case, we will not use all the 30 iterations, but we would have the option here. And this basically then constitutes of how long the algorithm runs. If you have a really large number here of number of minimal accepted samples, then the algorithm takes a bit longer. And if the number is smaller, then of course the algorithm takes less time. Okay, so this is the setup. Now let's actually run the algorithm. So we have to insert our graphs. So let's go back to our slide and see what we have to insert here. So here we are back at our 2 graphs, and I have already written down the edges of our graphs below so that we can see them directly. And as you can see, I put it also in the same format as we have to do it in the cloud. So let's first insert graph A. So we have the edges 4, 1, 1, 2, 1, 3, and 2, 3. So let's see if I can remember that. So we have 4, 1 as the first edge, 1, 2 as the second one, 1, 3 as the third one, and 2, 3 as the fourth one. Let's just check if that's correct. Perfect. Okay, now we do the same for the second graph, graph B. So 4, 1, 3, 4, 1, 3, 2, 3. 4, 1. Oh, actually, okay. 3, 4, 1, 3, and 2, 3. Just check. Okay. And now you can already see these 2 graphs, or maybe you've noticed before, they have very similar edges, but not exactly the same. So we can see there is a difference in the description. So maybe these 2 graphs will be isomorphic or maybe not. So you can still think about it, and I will just run this algorithm on the cloud, and then we will see what the cloud says. So I send API request, and we can see, great, the job is created. So now the algorithm is running on the cloud. And if we go back to our cloud, we can go to jobs, and there we will see that this job is created. So let's, we have it here already, graph isomorphism with the token cloud demo, and on the platform SimAlter, and it's running. So these like sample count jobs, these are the sub jobs, of which there's a maximum of 30 happening. And we can see they're still running. So we'll go back to the slides and then we come back in a second to check what the results are. Because I want to give you a second example. If we now add a third graph, so let me just move this. Here on we have 3 graphs. Now I've added a graph C. The graph C is slightly different to the graph A and B. So we also have, again, different edges. It also has 4 edges, so the number of edges is the same. So there's a possibility, again, that this graph is isomorphic to either graph A or to graph B, or that this graph is not isomorphic. So I'll invite you again to have a think about it. Does it have the same overall structure? So maybe you already have an idea. So let us put this graph also in the algorithm, but let's first have a look of what the result of our first algorithm was. So now let's refresh this here. We can see our graph algorithm is completed. So we can go back to our API, and actually we can go to graph isomorphisms results page, and we could here insert our token, our job ID, but actually it's much faster because we have the algorithm already here to just go on the I symbol. And then we get the job details. We can see, okay, the job is done. Perfect, everything worked. It took 1 minute and 17 seconds. Okay. And we can go down, we can see what was our inputs. And if we go to result, we see is isomorphic true. So the first 2 graphs, graph A and B, are actually isomorphic. So now you can check if you were correct. And I can tell you also this is the right result. The QPU, or in this case, the simulator of QPU Altair, did the right job. So the algorithm worked. So now let's go back to our IPA, and now let's go insert a new algorithm. So we had the 2 algorithms, the 2 graphs before, and let us now insert this third algorithm, graph C. So let us again delete all of this and all of this. And we have to put 2 lists here. And then inside the lists, we have, in our case, 4 edges on each graph. So there's one we can just copy. And we can now choose one of graph A and B because we already know that they are isomorphic. So let's take graph B. So we take 4, 1, 3, 4, 1, 3, 2, 3. So let's check if that's correct. Yep, perfect. And now as our second graph, we insert graph C. So this is 4, 2, 3, 4, 1, 3, 2, 1. So we do that here. 4, 2, 3, 4, 1, 2. And then what was the last one? 1, 3, and then 2, 1. Okay. 2, 1. Actually, and you will notice that if you play around with it, the order in which I insert these edges does not matter. And also the order within an edge, if it's 2, 4 or 4, 2, does not have any influence on the graph, because of course it's just one way of describing an edge, and there's no difference to the actual graph underlining it. So you can try it out and change some of these things, and you'll see that there's no change. So here again, let's change it to Altair. And then we can see all the other parameters have been the same. And we can, just to make sure that the token is the correct one, we'll go back to our tokens. We go to the cloud demo one, copy it. Normally it saves it as well. So maybe that was an unnecessary step in my case. But let's see. And now we can send a new API request. And okay, it worked. Perfect. So we can go back to the cloud, to jobs, and see if a new job has been created. And we see, yep, perfect. A second job of graph isomorphism has been created. Okay, we go back in a second just to look back at the graph. So what have we done? We've taken graph A and B and checked if they are isomorphic. And we found out, yes, they are. So that means in a mathematical sense, the overall structure of these two graphs are equivalent, even though they have maybe look slightly different on the page here, but what we're really interested in, they are the same. And now graph C might also be the same as both of them, or it might be different. Maybe you already have an idea. And we are now running an algorithm which checks if graph B and graph C are isomorphic. So let's have a look of how the algorithm is doing. And we can see, oh, directly is already completed. It didn't need even that many subjobs as the other one. So it was much faster. And we go back to the I symbol to see the job details. And we see, yes, it's completed, and it only took 1 second. So there's some variance in how long this algorithm takes. So this was really fast. And we can see they are not isomorphic. So because they're not isomorphic, the algorithm was really, really fast and could determine it. And that's absolutely correct. And I can explain you also why. So one reason why they are not isomorphic is because, as I mentioned in the beginning, it's all about the structure they have. And graph A and graph B both have the structure of 3 nodes being all together connected. And graph C does not have that structure. So that's already one indication they cannot be isomorphic. And that's actually enough. So this is what this algorithm can do and how it's implemented. And now I would like to talk to you a bit more about what these algorithms can actually be used for. So we'll start off with the graph algorithm, and then I'll also talk about the other algorithms I showed before. So here we have the same list as we had in the beginning. Close this for now. Okay, maybe not. So here we are at the top, you see the exact 5 algorithms I mentioned before. And here, of course, we have the graph isomorphism algorithm. And as I mentioned, a graph is just a network of a lot of nodes and edges, and it can represent a host of different things. So for example, one thing a graph could represent is a chip, a computer chip, like a classical computer chip. And then you could, if you create a new computer chip, you can also represent that as a graph. And then you compare it to the perfect graph you wanted. And if these two graphs are isomorphic, you know, good job, there's no errors, no faults in the chip you just built. But if the graph of the chip you built and the graph of the chip you wanted to build are not isomorphic, you directly know that there's some error. And this is a effective way to kind of test your procedures. And normally these graphs are much larger than the 4 nodes and 4 edges I just showed you. And then it's not really possible to just look at the 2 graphs and decide, yeah, they are isomorphic or they're not. So that's why it is super important to have an algorithm which can actually tell you that. And then there's other applications. So anything you can represent with a graph and where you're interested in knowing if 2 things have like similar properties, the graph isomorphism algorithm can be applied. So I invite you to think about what you're working on, and maybe there's an application for this algorithm, and then you can try it out directly using our toolbox. Okay, then let me just move on to the other algorithms and tell you about what you can use them for. So we have another graph algorithm called the dense subgraph identification. And basically what that does is it takes only one graph in and it finds out what are the most dense subgraphs. So that's something which, for example, is used in drug design if you want to find 2 molecules and how they can dock to each other, how they can be connect each other. There's a lot of different possibilities how they could, in theory, do it. And you could represent all of these possibilities by a graph, and then finding the densest subgraph of it gives you the best docking position for these two molecules. And so that's really important. If you want to design new drugs, you need to find the best ways how you can connect these molecules. So that's one application for the dense subgraph algorithm. But again, because graphs are so universal, any applications where you can represent your problem as a graph, and then you're interested in subgraphs of that, this algorithm could be very useful. Now, if we go back to the VQE-based algorithms, there again, there's loads of applications, and the list of use cases you see below, this also goes for the graph algorithm, is not an exhaustive list. It's just some examples I wanted to show you. So for the VQE algorithm, the most obvious use cases are related to the chemistry VQE, because it's already, you have the theme of where these use cases come from. So basically you calculate the ground state energy of a molecule. And so anywhere where you want to do something with these molecules, this might be super helpful. So for example, if you want to design a electric battery for electric cars, for example, they are a lot of times based on lithium. So here it is important to calculate the ground state energy of the molecules inside that battery, so that you can find out what's the best way of designing that battery so that you have the most efficient battery possible. So that would be one example how you could use the chemistry VQE one, but again, there's many, many more possibilities. Then for the custom VQE, here, as I said, you have a bit more flexibility of what kind of Hamiltonians you want to implement. So one thing, of course, is you could do the exact same thing as the chemistry one, but then it might be easier for you to use the chemistry toolbox algorithm. Or what you can do is you can solve differential equations. And I'm sure you know differential equations is a thing which are used in a lot of different scenarios. So for example, you could model a crack in a mechanical structure. So let's say I build a big wall and there's a small crack, and I want to see how this crack is going to evolve in the future. I can model that using differential equations. So I can now use the custom VQE to model this set of differential equations to understand if my wall is going to collapse or not. And there's many other applications where differential equations show up, and that's where you can use the custom VQE algorithm. Now for the CVA VQE, continuous value at risk variational quantum eigensolver, this, as I said, is optimized for combinatorial optimization problems, these QUBO problems. And here you have some specific use case I picked out, but again, any optimization problem which is of that form, of this binary optimization, this algorithm can solve. So one thing, for example, is in logistics warehouses, you can have something which is called multi-agent pathfinding. So basically, let's say you have a big warehouse and you have loads of robots which go around and find all the material you need and bring them to the production. There you have a lot of agents, all these robots, and they need to find the most optimal way of when is which robot going where. And that's a problem which can be solved using the CVA VQE algorithm. Another thing would be if we have for trains, we have these train units, and we want to have the best way of how many train units. So a train unit is like a train carriage. How many train carriages do I need for each train at what position, what place in my big train network, so that I have the best usage of my trains for the travelers needed. So again, this is a problem which needs to be optimized, and it's really difficult to optimize because it's so many variables. And again, here you can use the CVA VQE algorithm to solve that problem. Okay, so this is the overview I want to leave you with. So we have these 5 algorithms, and all of them have optimized for specific use cases. And I kind of group them into VQE algorithms and graph algorithms. So for now, this is what you can right now access at the toolbox. And I'll show you in a second also how you can access it if you haven't gotten a cloud account yet. And with all of these, there are some use cases which I showed you already, but there are many other use cases which I haven't talked about, and maybe there are even some use cases I don't know about, but you find out when you use the toolbox. And that's what we want to enable with this toolbox. We want to give you the chance to really focus on using the quantum algorithms which exist already today and try to find and make use of them rather than first spend a lot of time understanding how you can program them yourself. So we want to give you that on your hand so that you save a lot of time and can directly make use of these algorithms. Okay, so now let's have a look of how we can, okay, we've done the demo, how we can access the Quantum Toolbox. And Alexandra mentioned already, we have different plans on our cloud. So for example, the academic cloud, academic plan, where we just got a few more universities signed up. So with the academic plan, you can use the Quantum Toolbox. You have access to the Quantum Toolbox. And the academic plan is for anyone working in research at the university, for example, or who is a student themselves. And if you would like to get the academic plan, you can sign up at the cloud, and then you just have to prove that you are actually from such a university. And if you have any questions, just message Alexandra and she will help you with it. Then the second thing is, if you don't fall into that category, you can just sign up to the Pro plan, which is open to people outside of the academic world. And there you also can access the Quantum Toolbox. And if you, the third option, if you as a company, as an enterprise, are using the cloud a lot, it maybe makes sense to have an enterprise plan for the whole company. And there, of course, you also have access to the Quantum Toolbox, and there's some other features you get for it. But I wanted to focus on the Quantum Toolbox. So if you have the academic plan, the Pro plan, or the enterprise plan, you have access to the full Quantum Toolbox, and everything I did today, you can directly recreate. So I hope if you're already on one of these plans, you can go and play around with the toolbox a little bit. And if you're at the moment not on the toolbox, not on the cloud at all, or so far have the Explorer plan, maybe it's a good time to upgrade either to the academic or the Pro plan so that you can try out the Quantum Toolbox and see what you can do with it and if it's interesting for you. Okay, thank you very much. And we'll be back at another webinar soon. So keep an eye out, and I hope you enjoyed.
Thank you for joining us. Yeah, thank you for joining us. As Samuel said, you can reach out to me if you have any questions on the cloud, and if you need support, you can subscribe to the cloud for free. You can register for free and start exploring. And actually, it's without any compromise. You can work for free, and we won't ask you to share your bank account or credit card. And whatever you want to ask, you just open a ticket, and I will be supporting you. Okay. So thank you so much for joining us, and we hope to see you very soon on our next webinar and our next workshops. A hackathon that we call Locathon, and every other event that we organize for you. Thank you for joining us.
Thank you. Bye-bye.
Bye.